So, as you just said, I'm going to talk a little bit about how to optimize storage systems for the training of AI. Uh, well, many people already said this today, but AI is growing a lot, and it is entering in a lot of sectors and industries in our day-to-day lives, like ChatGPT, Copilot, or Gemini, that I believe mostly everyone has already used at least once, to automated driving cars, to the finance sector, where the market is being monitored, our investments are being automated, the health sector, where you have bots like Swords Health or Ferrum that are already investing and developing a lot of ways to help people. Cursor, there is a bot that is more connected to our field of software development. And in the middle of all of this, we have NVIDIA, that is developing both software and hardware for the development of these sort of models. It's very common for people that are developing this sort of models to invest in GPUs or TPUs that are hardware that is more focused in, instead of operating in one numerical unit, to use either vectors as a compute primitive in case of GPUs, or tensors that are matrices for TPUs, and so are more adapted to the sorts of calculations necessary for the machine learning process. However, if you're investing in a sort of hardware, you want to take the most profit out of it. So idle time is not ideal. So if you're not able to provide data at the same time that this hardware are consuming it, basically, then you're not taking full profit out of it. So we start having a bottleneck in the data acquisition. It can happen in between the CPU, where it's not being able to request it as with speed that it should be requesting it, or in the storage system itself, where it is not able to provide information at the required speed. So we started developing ways to optimize this. The first approach that I'm going to talk about operates a little in those second and third orange boxes in the decode and pre-process operations. Per default, it is done in the CPU. However, now we have methodologies like DALI that are enabling us to push these operations to the CPU. This enables CPU to start, for example, requesting the data sooner, so it can provide it more easily to be computed and processed later on. Another optimization is directly related to the way we are storing the data. So I assume most people already know this, but the storage system is thought to be more optimized if you read sequentially. So it's better if you read a lot of data in a sequential manner. However, usually datasets are not built like this. You have small files that are images and small files that have its metadata. So another way to optimize this process would be to merge some data from a lot of those files in only one big chunk of file. So instead of having thousands of files, you only have 100. So we have TF records and records IO that do this process, and the frameworks of machine learning are able to extract and map the data and metadata out of it. And the reads are much quicker and efficient. Another process would be data pre-processing decomposition. What is this? So let's say that for each epoch of machine learning training, you will read the entire data set. And every time you read, you'll have to decode and pre-process the data. However, you don't actually have to do it every single time, because the pre-processing and decoding will always be the same. So the approach that some people take is to save the after effect of these processes, so that once you do them once, you don't actually need to repeat them. That's great, because if you have 100 epochs to run, you only do it once. Another optimization that you can do using this is, let's imagine we have 2 jobs, or 100 of them, that are using the same data set and same decoding and preprocessing process. You can only decode it once for all of those jobs at the same time, and this saves a lot of weight out of the storage system and makes them easier and quicker. So another two optimizations. I'll couple them together even though they are different because it's really common for them to come together. Data loading parallelization and data prefetching. Data loading parallelization is related to, let's say I need to go to the data storage to read data A. I'm already making the trip, so I might as well take another data with me, data B. And data prefetching is taking data that I already know is going to be useful. So I know that I've already given data A to the model and it's trading with it, and the model hasn't requested another piece of data yet, but it will. So I'm already going to get it. So it's kind of easy to see how they relate to one another. If I'm going to read another piece of data, I'm going to read a piece of data that I know it's going to be missed. So they come together. Caching. So caching is more related to the storage itself. It's not cache of the operative system. It's a application build cache. And it's related to taking the process of going to storage, reading it, and saving it in a cache that you might build in memory or save in a layer in your storage. And this makes the next requests for the data once quicker, because accessing out of memory are a better is a bad word, because you can classify them based on different methodologies. So it's not necessarily better, but it's faster. So you can save it in memory, or you can save it in specific layers that are better. And this allows you to reduce the time that you waste reading the data. In this table, you can see some systems that are already doing this and being used in the market. As you can see, the second column is local, meaning these systems apply it to a local job. I have a computer, it is running a job, a machine learning job, and it's reading the data from storage. Multi-node can relate to two different scenarios. It's, for example, I might have two computers that have the same storage system, and each one of them is running a different job, but accessing the same data set in same storage. And the other scenario is distributed machine learning, where both of the computers are actually training the same model. However, they each are taking care of their own portion of the data set in each epoch and still accessing the same data set. As you can see, there are systems that are able to deal with both scenarios, but most times you have to choose one of them. The fourth column is about I would call it sort of setback. As you can see, most of these systems are either intrusive or framework specific. What does this mean? If I'm creating an optimization, I would like it to be applicable to all my training scripts. However, most times that's not the case. It implies that you'll have to change the way things are being done in the script. So you'll need to change the script itself. Specific means that it is not applicable to all the machine learning frameworks. You'll have to choose one, and only that one will be able or compatible with this optimization. The last column is about changing the loading order. Usually, machine learning model training scripts are the ones that set the order in which the data is being consumed, and it's done so that it's as random as possible. These systems don't follow that order. They follow the order that they either think is best for the final result and accuracy of the resulting model, or the one that is better for the return speed. Meaning, if I already have data A and you're requesting me data B, maybe it's easier for me to just give you data A. And sometimes they use a sort of thought beforehand impact. Meaning, in the first epoch, instead of just giving and taking data, they will analyze how impactful certain data was to the final accuracy of the model. And based on that, they will cache certain pieces of data that they deemed more impactful in a positive manner and give them more often. The last optimization that I'm going to talk about today is tiering. Tiering fully focuses on optimizing and taking advantage of the hierarchy system, hierarchy of the storage system. So let's say you have different layers in your storage. Some of them are going to be faster, but smaller might not be able to hold the entire dataset, and others might be bigger, so you can start there the dataset. However, they are slow. So what you can do is start by storing the dataset in the last one, and then distributing the entire dataset through the other layers. So starting through with the fastest ones, so you can have the best performance possible. In a multi-node setting, you can also do something that I find kind of fun, that let's say node 1 needs data A. It will push it to its local disk. That's, we are assuming, is smaller but really faster. That's the usual behavior in supercomputers, for example. And node 3 is also running a job and requires the same piece of data. Many times, it's quicker for node 3 to request it directly to node 1 instead of going all the way down to the shared file system. So this is also an optimization inside of tiering model. As before, we have a local and a multi-node approach. It's much more common in these sorts of systems to have systems compatible with both approaches. It's less common for them to be intrusive or specific. In this approach, usually they don't alter the order of in which the data is being loaded, mainly because we stopped having a benefit out of it, because in cache you had much more limited space to deal with. However, in this approach, you can count with multiple layers in your storage system, so you usually don't have that concern. However, this tends to be not always, but some systems tend to be incompatible with some of the previous optimizations that we talked before in the first part before caching, that were the loading optimizations per se, and some need additional resources other than the ones that we already required, which is not very positive since AI training is usually already quite expensive in terms of resources and resource intensive. So in conclusion, the AI requires really big data sets, and that's putting a load in our storage systems. So we needed to optimize this process of data obtention. I'm sorry, this is not the slides I was hoping for. Sorry. So we can count with decoding and preprocessing being pushed to the accelerators that are the GPUs and TPUs. We can count with the preprocessing decoupulation, and then on a more data obtention focused approach, you can count with prefetching, data loading parallelization. You can count with caching and tiering and data substitution. I wanted you guys to leave here with an idea of what is the benefit that we are taking from all of this. So firstly, by reducing the time that we are wasting or spending on the data acquisition itself, we are able to reduce the time that we spend training each model and enhance the hardware utilization. So we have less idle time. So this makes it more cost efficient, which is good at the enterprise level. Another benefit is if you're spending less time training with a specific configuration and hyperparameters, then you can train more times. And by training different configurations and hyperparameters, you are able to find better models at the end. So this enables us to support the rapid evolution that we are having right now in AI and keep up with the current public's demand. So that was my presentation. Thank you.